So he says, now there's my way of defining information, an algorithmic approach. He says it's mostly fruitful to discuss the quantity of information conveyed by the object X about object Y. It is not an accident that in the probabilistic approach, this has led to a generalization to the case of continuous variables, for which the entropy is infinite, but in large number of cases, again, he has a definition for the continuous case here, continuous variable. It says the real objects that we study are very complex, but the relationships between two separate objects diminishes as the schemas used to describe them become simpler. Yeah, sorry, Mike, you said something?
He's talking about, I can give some parallel with our modern data sets. Our modern data sets, which we are training LLMs on. You asked for LLMs, now you are getting your beloved LLMs near. So we are training our LLMs on tens of trillions of tokens, tens of trillions of words. This for me, it's quite infinite amount of data. Mm-hmm. And he asked, how can you do anything? How can you estimate something on such an enormous amount of data? And I think this fact motivated him to invent or to introduce this algorithmic complexity, which we are going to talk about.
Because now,
you can't do anything on this enormous amount of data.
Mm-hmm. And he says this new definition, which is IA of X given Y, he says that his definition might yield some different I's, different informations for the same problem, but they're bounded, right? So all of them will be smaller. The difference between all the possibilities are smaller than some constant.
Wait, why? Because you can go about in an algorithm, you can invent one algorithm, a second algorithm.
Yeah, exactly.
Yeah. Okay.
You come up with different algorithms, but they'll all roughly be the same.
Mm-hmm. Mm-hmm.
Up to the constant.
Yeah. It's bounded.
Yeah. Okay. Then he says, let's see. It says here, denote the length of the sequence n of x by lx, and we assume that there's some correspondence.
May I add some small remark? I think these 1, 2, 3 bullets are not very important.
Yeah.
He's writing here that not all of these
crimes are essential. Good point.
I think we need to proceed.
Yeah. There is the definition. At some point, it says here, fundamental theorem.
Yes.
Mm-hmm. Yeah.
And here he's talking about it as the relative complexity. You can continue. As the relative complexity of an object y with a given x, we will take the minimal length k of p of the program p for obtaining y from x.
Yes.
And this is the definition of the Kolmogorov complexity, the algorithmic complexity, which we are using today as well.
Yes, exactly. Yeah. And phi is the programming algorithm, right? Or method.
Yeah.
So let's unpack it to the listeners. If we go to the example of rooms, so if there's 5 rooms, I can write a program, right? That tells you, go to room number 2. If it's there, done. Else, go to room number, start with 1, then go number 2. If they're done, else, etc. So there's a program that I wrote that will get you to the key, and there's a length to it. Mm-hmm. This logarithm of the length, or the number of bits that you can compress this program that I wrote, is the complexity.
Nice.
Right? And then when I tell you it's either in room 1 or 2, so now the program you need to write is smaller.
Yeah.
Right? So the length of the program will be slower. So that's like the analogy to our case with the rooms and the keys.
Yeah.
Okay.
Make sense?
So just so I understand, okay? So when this complexity is 0, it means that we don't have, we know which room is it.
Exactly.
When the complexity is infinite, we can't write a program to find it.
Yeah.
Okay.
And here he's talking about relative Kolmogorov complexity, and beforehand he defines in a very similar way a non-relative on a standard Kolmogorov complexity of X. It is the same definition. You just don't condition by Y, but
Yeah.
it is the same. And I want to give a small explanation.
Yeah, perfect.
For example, you have a random sequence of bits. Okay, a random sequence of bits. In order to write a program, let's think about some Python program. No, not Python. Python is a too high-level program. Let's think about some abstract programming language. But in order to generate this sequence, I need to write a very long program. Why? Because there is no connection between zeros and ones. Okay, and we need a very long program which probably will generate zeros and ones just like in this sequence. This is the first case, uniform distribution. Now let's assume that you have 99% of ones and 1% of zeros. Okay, the program to generate this sequence should be much shorter, because almost what you get, 99% of what you got, are just ones. So you can imagine that the algorithm, I'm not a programmer, I'm not sure it is a good name for it, algorithm to generate the each sequence should be much shorter, because you mostly have ones. For example, if you have only ones, then the Kolmogorov complexity is 0, because I don't know 0. You need just to give a number 1, you know. But this is the difference, you know. And we will maybe talk about later. I think Daniel knows what is Solomonov complexity, and it is related. But let's leave it for. Let's discuss it a bit later.
Mike, I have a question.
Yeah.
You have a PhD in math. Which course did you take, if at all, when you learned about Kolmogorov complexity?
I'm not sure it was part of some course. Maybe there is information theory course which I got which I took in the Technion in the electrical engineering faculty.
Yeah.
Without grade, so I've never done exams. I think so in the last lecture, but I'm not sure. What I can remember that I learned about Solomonov complexity on some course in the computer science.
Yeah, so I'll give a few words just. Actually, prior to this paper, Ray Solomonov also developed similar ideas. And I think that Kolmogorov later acknowledged he wasn't aware of Solomonov work. And like it was just a year prior. And Solomonov had more general about Solomonov induction. He tried to solve even a more difficult problem than we're talking about here.
Yeah, by the way, he was talking about for each sequence. He was talking about the probability that each sequence would be created with some universal Turing machine,
yeah,
like that. And in this way, this Kolmogorov complexity and Solomonov complexity are inversely related. You know, the Kolmogorov complexity grows, and for the more random is our sequence, the more uniform distributed is our sequence. The Kolmogorov complexity grows, but I think the Solomonov complexity is going down.
I'm not sure. I thought it was similar.
Yeah,
I'm not sure.
Okay, I think they are related as minus log 2. but I don't remember. Okay, our listeners can check it. Can ask some LLM.
It's less relevant to this paper.
I have a question to both of you. What do you think we're doing in modern day LLM? The probabilistic method, or by training the LLM, the probabilistic or the algorithmic, or a combination of both?
Actually, it is quite non-trivial question. I think there is some term which is called MDL, minimal
description length.
Minimal description length, which is very related to Kolmogorov complexity, which equals of the size of the program we can encode our information, and the size of our information after the encoded this program is more about compression. And here it is related to how we train our LLMs. We have a size or complexity of our model, which is governed in some way by regularization, and we want to build some model which somehow explains our data. And what do I mean by explains our data? Which makes this log likelihood probability relatively high. So we want to encode we want to understand our data, and in the same time we want to do it with the simplest model we can. So it is, I don't know how, but I have a feeling which is also connected to a COM raiser. The simplest of all possible explanation I usually correct, but I can explain it clearly.
I think actually, if you talked about Occam's razor, I think Solomonov induction is generalization of Occam's razor.
Okay.
In some sense. And I think related to your question here, my view that this is more, I don't know if useful, but intuitively more useful, because this algorithmic, the algorithmic approach is more about compression, right? Because we're trying to write a program and calculate like the number of bits or the length or how compressed this program is.
Yes.
So from an intuition perspective, I think it gives more intuition, because like LLMs compress like all the data that they were trained on to a degree. And I think it's also another connection that I thought about is the bias variance trade-off we have in machine learning.
Yeah.
Right, because simpler models, meaning lower complexity, by definition, the program, like the model, is smaller.
Yeah.
It has less variables. They generalize better oftentimes. And right, so you have like this bias variance trade-off related to this Kolmogorov complexity. So that's
by the way, a very small remark about smaller models tend to have smaller complexity. The large models are not always don't always tend to be higher complexity. They have a double descent, very interesting phenomena, which you have a very. We are working in our machine learning, our deep learning. We are working in a very over-parameterized regime. So we are working with the huge models, but the real complexity of these models is not very high, because you probably heard about the lottery ticket
hypothesis.
Every neural net contains much smaller neural net which is doing the same. But if you start from the smaller size, you can't train properly or on your data. But still, not every big model have a very large, let's say, complexity.
Okay, so we're gonna continue. We're close to the last chapter, which is the conclusion. But before the conclusion, he says that, in his opinion, this new definition of complexity, like instead of entropy or something like that, which is more probabilistic, the new definition of complexity makes more sense if you think about books, right? If you think about biology. And today, a lot of people talking about complex systems and physicists going into that. So maybe he was one of the original thinkers in that area.
Definitely.
Complex systems, yeah, comes from complexity. And he says, like, now it makes much more sense to talk about complexity estimates of a book or whatever. He says, I believe that the approach proposed here yields in principle a correct definition of the quantity of hereditary information, although it would be difficult to obtain a reliable estimate of this quantity. So it's interesting, like he's motivated by what makes sense, what's more intuitive,
Yeah.
Which is lovely. Okay, so now the conclusion. The concept discussed in the last chapter is the complexity definition have one important disadvantage. It says that they do not allow for the difficulty of preparing a program P for passing from an object X to an object Y. So it says maybe coding, this program, the algorithm, would take a lot of compute, or maybe infinite time or whatever, right? That's his point.
Yeah, by the way, I think there's an interesting link between this observation and the generative models. What we are doing in our generative models, we are starting with some basic distribution, which in most cases is a Gaussian distribution, and we want to train our neural net. What is our neural net? It's type of our program, because by means of this neural net, we are going to generate a new data. And here, this effort, this difficulty is, like you said, it's just the amount of compute you need to build this this machine or this program, which would allow you to generate new data. So this and I think this is very important, because we are training a huge models now, and this difficulty is the amount of electricity, amount of power you need to train your model. So I think it is of quite big importance even now.
Got it. Yeah, makes sense. Again, to us, maybe we're used to think about like complexity and information, but like now it's more formalized, I guess, after this paper. What do you think? Like in your mind, after reading it?
This is a very important concept. I'm not sure we are using it straightforwardly. They are using it as a means of explaining stuff. For example, this difficulty of training a neural net, which is also related. Okay, you trained a very good neural net which can generate your videos from text, but you needed the amount of power for San Francisco for 1 year for it. So
yes,
so all this stuff. So you got a very, for example, you got very efficient neural net which you can use to generate your videos, but the amount of compute you spend for it is very high, and all this MDL stuff, which is also related to Kolmogorov complexity, although we are not using it in our calculation, but it is still in our subconscious layer. We know it, and we try to understand stuff with the help of it. So I think it's just very important concept which help us to understand stuff better in machine learning, in big data. But I'm not sure it is better formalized. By the way, there is very interesting lecture about it. I'm not sure that I managed to comprehend it, by Ilya Sluskova from OpenAI, the short 40 minutes lecture. I think 1 year from 1 year ago.
What is the name of the lecture? If our
I don't
listeners,
remember. You need you can just write googling Ilya Slutscover Kolmogorov complexity.
Okay, we'll put it in the links.
Yeah. I think it can
I'll find it and I'll put it in the links.
Yeah. But this lecture, it is not very mathematic, but the concepts he's talking about in plain English are quite complex, and I'm not sure I managed to fully comprehend it. And he's talking just about these concepts.
Yeah, definitely relevant for modern day machine learning stuff, especially the connection with the time that he does. That at least he hints for future work about this.
Cool. So we'll link it in the description, in the comments. And in my view, I do like this paper because again, we did Shannon, and I didn't feel like how it really relates exactly to machine learning and what we do as practitioners. Also now, it's not like I use it as a tool, right? It's not like the PCA paper.
Yeah.
It's more like a framework of thinking about problems, which that's how I look at it. And I think it's a nice progression. So later when we'll stumble upon future papers, we'll be able to look with this new view of complexity on those problems.
By the way, Daniel, one maybe interesting thing which is worth checking, how all this Kolmogorov complexity is connected to VC dimension, to Wapnick-Chernovensky dimension of the model, because I'm not sure. I don't want to talk some nonsense. I'm not sure I understand it in sufficient depth, but I think there is. I'm sure there is some relation.
There is relation, yeah, because I know there's relations between VC dimension and Solomonov induction.
Yeah.
So for sure, somehow it's connected here. But we'll get to VC dimension. Probably it will take us 2 years or something, because it's 90 something. It was in
maybe
Vapnik. It was Vapnik, right?
Wapnick-Chernovensky.
Yeah, I think it's 90 or something.
90, okay, maybe. I don't remember.
But when we'll get there, we'll have the history, so it will be cool. That's why I'm excited.
Yes. Question: in terms of history and the zeitgeist of this era, the 60s in Russia, in Soviet Union,
Woodstock.
Yeah. Did they have access to other like American papers or other European papers that were coming out in this?
I'm not sure. First of all, frankly, I can tell it. I don't know. I don't know for sure, but I can presume that there were some scientists, some mathematicians with some good relations with the different branches of Communist Party, and some which had some some protection vitamin, that I think they got access to these papers, and so I'm pretty sure that the mathematician of the caliber of Kolmogorov, I'm pretty sure he knew about Shannon and about fission, all these papers about information and statistical papers. I'm 99% sure that he knew it, but I don't think that every mathematician, for example, in Moscow and St. Petersburg, I think they got it because there are huge differences between the universities, between the institutes in Moscow, St. Petersburg, and almost all other cities in Russia, except for Moscow and St. Petersburg. Almost there are 3 or 4 good universities in Russia, but the best ones, a couple of dozens, were located in Moscow and St. Petersburg. So what is my point? That I think that some mathematician from Moscow and St. Petersburg University got this access to foreign papers. Most of the mathematicians, I'm not sure. I think they were talking. Okay, they have phones. It was 60s, not 30s, not 20s. So
Yes.
I guess somehow many of them knew, but
I think he traveled the world. I think Kolmogorov visited Europe and stuff. I'm pretty sure.
So
what
he was
about the other way? What about the other way? Do we know at what year, let's say, American mathematicians saw this paper first time?
Maybe it's 68 because that's the translation is from
That's the
68.
Yeah,
So 3 years after.
I'm not sure because there are some people in USSR who knew English. I think it worked. By the way,
Here's the journal.
Yes, but I think that in the inverse direction, it worked. I think the American scientists knew about the Russian Scientist Journal. I'm pretty sure because they were more open. But
the flow of information is not symmetric.
But I have to say that maybe I'm totally wrong about it. This is my opinion.
Yeah.
This is what I think about it. It relies on some information I have, but this information is not full.
No, that was a good question. It is interesting, like each paper, to think about the time it was embedded, the society it was written in. There's so many ways to look at it and think about it.
By the way, I just came across in my mind some funny fact. There is a Gauss formula. There is some integral, but in Russia, when I studied in Russia, I studied as Ostrogradsky Gauss, and then I came to Israel and I asked guys, what do you know this formula? Who's Ostrogradsky? We don't know who is it. This is he's totally unknown mathematician. It is called Gauss formula, the Gauss formula, not Ostrogradsky. So I guess there was no complete and full flow of information there.
Yeah. Perfect. So
definitely not complete. Even without the communist or communism there, the translation was not very prevalent, I guess, back in the day. So a lot of information was stayed in Russian, right?
Yeah.
Yeah.
I think that most of the Russian journals in the 60s, not very famous journals. I think this journal of what is its name?
In Russian, it's
Information. Maybe it is a very famous journal, and it was translated. I guess there were a lot of other journals which were not translated, and we will never know what was written there. But at least now we have more or less full access to all the information what is going on in the world because of the internet so now we are in much better position. So let's utilize it.
All right.
Perfect. So on this positive note, we're gonna end today. So thank you, Mike. Thank you, Nir. Thank you to the audience. Feel free to like, subscribe, and all the podcast apps and stuff. And see you next week.
Bye bye.
Bye, guys. Pleasure as always. Bye bye.